Hello students, today's topic is limit at infinity. That is, we want to know the value of our function as x approaches a very large positive number or a very large negative number. The limit at infinity is important when we are sketching the graph of a rational function. We evaluate the limit of a rational function at infinity to find the horizontal asymptote of the function. Let's start with a few examples and evaluate the limit at infinity. To evaluate the limit of a function at infinity, we want to divide each term of our function by the variable that has the largest exponent in the denominator, simplify our function, then evaluate the limit of the function as x approaches positive or negative infinity. We will start with example 1. We want to evaluate the limit of our function 9x to the 7 minus 2x squared plus 12 all over 3x to the 7 plus x minus 42 as x approaches positive infinity. Notice x to the 7 is the variable with the largest exponent in the denominator. So we want to divide each term in our function by x to the 7. This is going to equal to the limit of our function as x approaches infinity. Now we have 9x to the 7 minus 2x squared plus 12, and we want to divide each term by x to the 7. We will do the same in the denominator. We have 3x to the 7 plus x minus 42, and we want to divide each term by x to the 7. Now, we want to simplify our function. This is going to equal to the limit of our simplified function as x approaches infinity. 9x to the 7 in the numerator divided by x to the 7 will just give me 9, minus 2x squared divided by x to the 7 will be 2 over x to the 5th plus 12 over x to the 7. In the denominator, we have 3x to the 7 divided by x to the 7. We'll just simplify to 3 plus 1 over x to the 6 minus 42 over x to the 7. Now, what will happen to the terms that are divided by x to a power as x approaches a very large positive number? Now try that on your calculator. Enter -2 over a very large positive number. You will notice that your number is approaching 0. The same thing with 12 over x to the 7, 1 over x to the 6, and -42 over x to the 7. So all these terms, as x will approach a very large positive number, will approach 0. And we are left with 9 over 3. So the limit of our function as x approaches infinity is 9 over 3. And this simplified to 3. Moving to problem 2, we want to evaluate the limit of our function 4x cubed plus x minus 5 all over x to the 6 minus x to the 3rd minus 2x squared as x approaches negative infinity this time. We notice that x to the 6 is a variable with the largest exponent in the denominator, and we want to divide each term in our function by x to the 6. So this is going to give me the limit of my function as x approaches to negative infinity, and my function will be 4x cubed plus x minus 5, each term divided by x to the 6. The same in the denominator, I have x to the 6 minus x cubed minus 2x squared. And each term will be divided by x to the 6. Simplifying my function, I will have the limit of my simplified function as x approaches negative infinity. My simplifying function will be 4 over x cubed plus 1 over x to the 5th minus 5 over x to the 6th. X to the 6 over x to the 6 in the denominator will simplify to 1 minus 1 over x cubed minus 2 over x to the 4th. Again, we notice that each term divided by x to a power, as x approaches a very large negative number this time, each term will approach 0. And I am left with 0 in the numerator. These terms will approach 0 in the denominator. I'm left with 1. 0 divided by any non-zero number is just 0. So the limit of my given function as x approaches negative infinity is 0. Now, I want to start with problem 3. Problem 3, I have to evaluate the function 12x to the 6, the limit of the function 12x to the 6 plus 7x squared all over 11x to the 5th minus 31 as x approaches positive infinity. Here I have x to the 5th, the variable with the largest exponent in the denominator, and I want to divide each term in my function by x to the 5th. This is going to equal to the limit of my function 12x to the 6 plus 7x squared, and I want to divide each term by x to the 5th in the numerator and do the same in the denominator. So the limit of my function as x approaches positive infinity. Now I want to simplify. This will give me the limit of my simplified function as x approaches positive infinity. My simplified function here is 12x plus 7 over x cubed over 11 minus 31 over x to the 5th. Again, the terms that are divided by x to a power, as x approaches a very large positive number, will approach 0. So this term will approach 0, and the term in the denominator, negative 31 over x to the 5th, will approach 0. And I'm left with the limit as x approaches infinity, the limit of my function 12 over 11x as x approaches infinity. Now I can bring the 12 over 11 out, and then I'm left with the limit of x as x approaches infinity. So the limit of x as x approaches infinity, this is going to give me infinity. A constant multiplied by infinity, a very large number, is just going to be infinity. So the limit of my function as x approaches positive infinity is infinity. Notice when we evaluate the limit of a rational function at infinity, we will always have one of these three cases. Case 1, when the leading terms in the numerator and denominator have the same variable with the same exponents, our limit will always be the quotient of their coefficients. In this case, we had 9/3 simplified to 3. Case 2, when the leading term in the numerator have a variable with the exponent less than the exponent of the variable in the leading term in the denominator, the limit will always be 0. And case 3, when we have the leading term in the numerator has a variable with exponent larger than the exponent of the variable in the leading term in the denominator, the limit will always be infinity. Now, sketching the rational function in problem 1, we see that the function has a horizontal asymptote at y equals to 3 as x approaches infinity, right here. So when we evaluate the limit of a rational function at infinity, we are in fact finding the horizontal asymptote of the function. Similarly, the graph of the rational function in problem 2 has a horizontal asymptote at y equals to 0 as x approaches negative infinity. Finally, the graph of the third problem shows that the rational function does not have a horizontal asymptote when x approaches positive infinity. I recommend you graph these and other random rational functions using any graphing tool to better visualize the results of each one of the 3 cases when the limit of a rational function is evaluated at infinity. Hope you found this video helpful. See you next time.